Assalamualaikum and hi, I'm Nur Fikriat Masari Bintali dan 2023165611. So today I'm going to present about Introduction and Equation 1. As you can see here, this is the introduction for this topic and equation. But the first thing first, you need to know what is meaning of wave propagation. Wave propagation in a solid happens when atoms vibrate around their fixed position and pass energy from one atom to the next. If the wavelength of the wave is much larger than the distance between atoms, the solid behave like a continuous material and the wave travels smoothly. The speed of the wave mainly depends on the material properties. Stiffer materials like metal allow waves to move faster, while soft materials like rubber slow the wave down. This is the problem statement for this topic and equation. Firstly, to explain how wave velocity behaves in a solid when the wavelength is much larger than the interatomic spacing using the dispersion relation. Second, to identify the factor affecting wave velocity by comparing two different types of solid material. Moving to the equation 1, using the dispersion relation and well-labeled diagram, explain the velocity of wave propagation in a continuous solid medium when the wavelength is much larger than the interatomic spacing. Also, discuss the factor that influence the wave velocity by comparing two different types of solid material. As you can see here, this is the image explain how waves travel through the solid and what affect their speed. First, look at the atomic chain at the top left. In a solid, atoms are arranged in a regular lattice with a spacing called A when the wavelength of a wave is much larger than this atomic spacing. The solid behaves like a continuous medium. In this long wavelength limit, the wave travels smoothly through the material. In this region, the dispersion relation is a linear, meaning angular frequency W is directly proportional to the wave vector k. This is written as W equal V times k, where V is the wave velocity. Now, look at the graph below. The vertical axis is angular frequency W and the horizontal axis is the wave vector k. The straight line portion show the linear region. The slope of this line represents the wave velocity. Because the line is a straight, the wave velocity is a constant. This also means the phase velocity and the group velocity are equal in this region. On the right side of this image, we see factors that affect wave velocity in a different material. Metal, like steel, have a strong atomic bonding and a high elastic modulus. Even though they are dense, their stiffness dominates, so wave travel very fast through them. In contrast, polymer or rubber have weak intermolecular bonding and a low elastic modulus. Even though they are lighter, the lack of the stiffness causes wave to travel much more slowly. So, overall, this image shows that wave speed in a solid depends mainly on elastic stiffness and bonding strength, and that in the long wavelength limit, wave travels with a constant velocity. That's all for me. Thank you.
Assalamualaikum and good day. I greet to Madam Suhaida and my fellows. My name is Nur Hanisha Zani binti Muhammad Nasli and my student ID is 202336851. Next, I will explain about the application based on the question. Now, let's dive into a comparison between two solid materials, steel and rubber. Both materials have distinct physical properties that significantly influence how waves propagate through them. We will compare their wave velocity and the key factors at particularly stiffness and density. Material 1 is steel. Steel is stiff and dense with a high Young's modulus E. This allows faster wave propagation. The high stiffness overcomes the effect of its high density, enabling faster wave travel. Material 2 is rubber. Rubber has a low stiffness E and a lower density than steel. Despite the lower density, its low stiffness slows down wave propagation. In summary, steel's higher stiffness results in faster wave propagation compared to rubber, where low stiffness is the key factor slowing down the wave velocity. Next, I will summarize in the form of mapping concept on how to solve the problem that has been explained by Victoria just now. Let's walk through this concept map on wave propagation in solids. At the center, we have wave propagation in a continuous solid medium. This is our main topic and we will break it down into key concepts. Firstly, dispersion relation. This describes how the frequency omega related to the wave factor k. The formula is omega equal to vkk, where vk is the wave velocity. This relation helps us understand on how waves travel in the different materials. Number 2, wave velocity. Wave velocity Vk depends on the material properties like Young modulus E and density ρ. The formula Vk equivalent to the square root E over ρ shows that stiffer and denser materials typically have faster wave propagation. And thirdly, material properties. Stiffness E. A stiffer material transmits wave faster, while density ρ, a denser material, resists motion, slowing down the wave propagation. And the fourth, comparison of materials. Steel has high stiffness and density, leading to faster wave propagation, while rubber has lower stiffness and density, resulting in slower wave propagation. And conclusion, the wave velocity in solids is influenced primarily by the material stiffness and the density as shown in the formula Vk equivalent to the square root E over ρ. Last but not least, let's explore on how the concept of wave propagation in solids plays a crucial role in various fields. Firstly, medical applications. In ultrasound imaging, wave propagation is used to create a detailed image of the body's internal structures. By understanding on how sound waves travel through different tissues, we can improve diagnosis accuracy. Therapeutic ultrasound uses wave propagation to treat the condition by targeting tissue with focused sound wave, aiding in pain relief and healing. Secondly, robotics and automation. In robotics, wave propagation helps with vibration sensing and acoustic communication between robots. By understanding how wave travel through material, robot can navigate, detect obstacles, and even communicate in environments where traditional signals may not work. Wave sensor can detect changes in material properties, improving quality control and automatic efficiency. And lastly, non-destructive testing (NDT). In NDT, wave propagation techniques like ultrasonic testing allow engineers to inspect materials without damaging them. Understanding how wave propagation through solid materials helps detect loss in critical structure like pipelines, aircraft, and bridges, ensuring safety and reliability. In all these fields, knowledge of wave propagation enhances accuracy, safety, and performance, making it a foundational concept in modern technology. I think that's all from me and my friends. Thank you for listening.